Hi there. This is the sound of an oboe. And this is the sound of a trumpet. The pitch and volume of these two sounds are the same, and yet you clearly hear a difference. They differ in timbre. Because of this, we can distinguish between these instruments. Now, we know how to describe pitch and volume in numbers. Pitch can be described by frequency, and volume by the amplitude of the sound wave. But how to quantify timbre? This seems very elusive, and yet there is a way. Remember that sound is a pressure wave. If we plot pressure as function of time for both the oboe and the trumpet, you already clearly see a difference in the shapes of the graphs. But still, shape is a bit vague, so what to do? Well, what helps here is the theory of so-called Fourier analysis. It is named after its inventor, Jean-Baptiste Joseph Fourier, who was a French mathematician born in the 18th century. The theory roughly states the following. Suppose we have a periodic function with frequency f. Then this can be written as the sum of sines and cosines with frequencies f, 2f, 3f, etc. The shape of the function determines the precise amplitude of each sine and cosine. So how does this work? Well, let's take a sine function with the same frequency as the wave. This is given by the expression sine of 2 times pi times f times t. To keep the subsequent formula simple, I replace 2 times pi times f by omega. The idea is now to choose the amplitudes such that the sine best fits the original wave function. What that means precisely is a bit technical, and I will not explain it here. We do the same for the cosine. In this example, it turns out that we need a smaller amplitude for the cosine. The sum of the sine and the cosine already approximate the original function. To improve the approximation, we add a sine and a cosine of double frequency, each with such an amplitude that the sum best fits the sound function. And then we continue in this way by adding sines and cosines of 3 times the frequency, etc. The more frequencies you take, the better the shape is approximated. And in the limit, you obtain an infinite sum called the Fourier series. When it comes to sound, you need only finitely many terms in practice, since the human ear is insensitive to high frequencies. The only choices you have to make are the amplitudes. In fact, the shape of the graph is precisely encoded by these amplitudes. And moreover, the more frequencies we take into account, the better the shape is approximated. Let's see how this works for the instruments. First, the oboe. Following Fourier, we can write the sound wave as a sum of sines and cosines with frequencies that are multiples of the frequency of the wave. The more frequencies we take, the better the approximation. And in the limit, we exactly recover the sound wave. We can do the same for the trumpet. Again, the more frequencies, the better the approximation, and in the limit, we recover the sound wave. Now you see that we have to take the amplitudes differently for different instruments. For both instruments, the set of amplitudes precisely encodes the shape of the graph. And so these amplitudes describe the timbre of the sound. The theory of Fourier analysis is of fundamental importance in acoustics, optics, and signal processing, but there's more. The applications are actually not limited to analyzing periodic signals. And in fact, Fourier himself was not studying sound or light, but rather heat conduction through a material. If you have an iron rod and heat it at some point, how does the temperature in each point of the rod change over time? You may be surprised to learn that Fourier could solve this by writing the temperature profile in the rod as a Fourier series. The question that remains is, of course, how to find the amplitudes in the Fourier series. This you will learn in the lectures to come.